All right, we're going to start our unit on magnets. There are some important things for you to know. So what do you need to know? Magnets are used in many ways. You should know a few. Take a minute. Think of some ways that magnets may be used. Okay, well, all magnets have a north and south pole, and each magnet has a magnetic field around it. Different shaped magnets make different shaped magnetic fields. So these are the three concepts that we're really going to focus in on today. Magnets. A magnet will pull some metals towards itself. Metals that contain iron, nickel, and cobalt are magnetic. In other words, a magnet will pull them. Some examples of that are, here is my magnet, just a regular magnet. And this right here is made out of some type of metal, and it is attracted to my magnet. All right. So usually metals that have iron or nickel in them or cobalt are magnetic, so the magnets can pull them to them. All right. So again, here's my magnet, here's the metal, and whoo, jumped right over, didn't it? Ready? One more time. Thanks. Think back to when I asked you of some ways that magnets are used. Let's talk about a few ways that magnets are used. Okay, so which of the following items in a home use a magnet? Blender, washer, dryer, radio, can opener, dishwasher, refrigerator, doorbell, compass. If you said they all do, then you have the answer correct. All of those items have a magnet inside of them and use that magnet to help them work. Magnets have poles. No, we're not traveling to the North Pole or the South Pole to visit penguins and polar bears. But they do have a north side and they have a south side. Okay, just like the Earth has a north and south pole, magnets have two poles. If you take a bar magnet and hang it from a string, the end that points north is the magnet's north pole, and the end that hangs south is its south pole. This is because the Earth is actually a huge magnet itself. That means that the magnet is actually being attracted to the Earth, which is just one huge magnet. Similar magnetic poles repel, while opposite magnetic poles attract. So you ever heard that saying, opposites attract? Well, that's true with magnets. North and south attract. But if it's south and south, they repel or get away from each other. And I'll show you an example of that now. So I have two magnets, and let's see. Oh, they attracted. So this must be a north and a south because they went together. I don't even have to hold them together. Now, if I flip this over, I wonder if the same thing will happen. I'm trying to push them together, but I can't. That means they have the same poles. Either they're both north and north, or they're both south and south. Because opposites attract. They attract each other. But if they're the same, they don't want to go together. Ugh, can't do it. Just like we said, Earth has a large magnetic field, so do magnets, large and small. Every magnet has a magnetic field around it. It can be thought of a line of force running from the north end of the magnet to the south end of the magnet. Earth's magnetic field is what causes the needle of a compass to point north and south. And I can kind of demonstrate that. I have a round magnet here, and I have a bar magnet. It's pretty small. But have you ever held up a magnet and you put them together, and all of a sudden you let go, and it just jumps right out of your hands? Because it's within that field of magnetic force. So right now, and they are opposite, there's one that's north and there's one that's south. Right now, they get into that field and they attract. Now, if I flipped one over so that I have the same, I can actually feel that. And later on, I would get two magnets and try to push them together so you can actually feel that invisible force field that's around it. It's almost like Star Wars, they're battling each other. Oh! Okay, but you can feel the field around it. You can kind of bounce on it. It kind of has a spongy feel to it. And then if you turn it again to north and south, remember opposites attract, you get it close enough, boop, it just jumps. And I'll do that with other pieces of metal as well. Here I have my paper clip. If I get close enough, look at it, it just, oh, slowly, I'm not making it do that. It does it itself because of that magnetic force field around it. Boop. It just jumped right at the other magnets. So this is an image of the magnetic field of a bar magnet because we can't actually see it in the classroom. But as you can see, that field is moving here from the north to the south, north to south, because they want to attract each other. And these are pushing out away from one another. Okay, so if I put a south on this side, it would be pushing in the opposite direction, and they would actually force each other apart. But let's say I put a south over here. Okay, again, this guy is trying to pull them in, this one is going out, so all of a sudden that south will connect right to the end of it. All right. Here's just another image of the magnetic field of a horseshoe magnet. Horseshoe magnets are very neat. They're actually used a lot in industries. You can actually see the north and south labeled on there. And they're used to pick up items like large pieces of metal. But what's nice is that that magnetic field is only on the bottom, and that on the top you don't have to worry about it snapping to any other piece of metal or attracting anything. So this right here is a horseshoe magnet. Magnetic fields can also be seen using iron fillings. So scientists use iron fillings to explore these invisible fields. This is a picture below that shows iron fillings around a horseshoe magnet. So you can see those force fields. Down here, it's very, very strong, so all those iron fillings are being attracted to it down here, but up here it's pushing away, so you don't have to worry about it connecting to something. Have you ever played that game where you have a picture of a person and you have a little magnet underneath, and you can give them a little mustache, you can add little eyebrows to it, and then when you take the magnet away and you can shake it up, and you can redraw your picture over again. And this is the same thing here, where the scientists are using the iron fillings to show you. So magnetic fields, again, this shows two bar magnets that were placed near one another. We can see that these magnets have the same poles facing each other because the iron fillings are pushing away from each other. So it's either going to be both south and south, or both north and north, because they're pushing each other away. They're saying, get away, because remember, only the opposites attract. What is the missing pole? Based on the pictures that we saw, if you notice that the iron fillings are attaching there, but they're kind of repelling outward. So my guess is that this is a north pole, because they're not attracting to each other. They're actually repelling away from each other. What is this missing pole? But notice here that the lines are connecting to one another. So my guess is that they want to bring each other together, so that this would be a south pole. Remember? Here is our last trial. Can you guess what this missing magnetic pole is? If this is north, this side must be south, because there's always two poles. So with that information, can you guess the missing pole of the bar? If you guess that it has to be a north, then you would be correct. This is the end of our presentation on magnets. You can go back and study it at any time, but again, the important points for us to know is that all magnets have a north and south pole, that opposite magnets attract, and if it's the same pole, north to north and south to south, they repel one another. And that magnets are used to help us with many jobs, like your dryer, your radio, all of those run off of magnets. And we'll talk a little bit more about that as we get further into this topic.